Okay, just one question to warm up, to just to remember certain things. This question. So we have a spherical shell, and the question is inside the spherical shell, what does the electric field do? Is it constant and zero, constant and non-zero? Does it grow linearly or some other functional form? Or you don't know? You cannot even determine using Gauss law. This question only. No, it's not a conductor. It's a shell. Uniformly charged shell. What is the electric field inside? Here we have this uniformly charged spherical shell. What does the electric field inside do? Is it constant and zero? Is it constant but has a non-zero value? We don't read, we will not be discussing what that non-zero value is. Is it linear? Does it grow linearly as you go away from the center? Or does it have some other functional, maybe more complicated dependence which can be determined using Gauss law? Or can't it even be determined by the Gauss law? Now, as you go from the center towards the surface, you are somewhere inside. What is the electric field inside? No. Well, the shell is charged. There is a uniform charge on the shell. How many of you think it is 1? How many of you think it is 2? How many of you think it is 3? 4? And how many of you think that it cannot be determined? Yes, 2. Why 2? Why is it constant and non-zero? I saw one hand over there. How many of you think that it's constant but non-zero? Okay, no hands. Why can't it be determined? Okay, so assuming we are drawing a Gauss surface. Okay, a spherical Gauss surface. Okay. Okay, which is 0. No, Q enclosed is 0. There is no charge inside. Okay, so it's constant and 0. What about the potential? What is the potential inside? And we are defining the potential at infinity to be 0. And the choices are still the same. What is the potential inside the spherical shell? Is it constant and 0? Is it constant but non-zero? Does it grow linearly, or does it have some other functional dependence, or it's so complicated that even with the Gauss law it cannot be determined? The potential. So how many of you think it is constant and 0? How many of you think it's constant but non-zero? How many think it grows linearly? Okay, take your time. After you use your time, 1, 2, 3, 4, and 5. This is 1. There is 2. There is 3, 4, and 5, and nobody is sitting down. Two is over there. The question is now, what is the potential of any point inside this shell? And to define the potential, we choose the infinity as our reference point, and we are assuming that the potential at infinity is 0. This is 1, this is 2, 3, 4, 5. Well, the potential at infinity is 0. The potential at the center, sorry? No, there's no charge. There's only charge on the shell. There is no charge inside the shell. And the question is, what is the potential inside the shell? Two is over there. You are losing people. Two is over here. No, the question is this one. What is the potential in the center? Not in the center, inside this shell. Of course, to define the potential, you have to take a reference point. And the reference point is usually chosen to be at infinity. At infinity, the potential is defined to be 0. Now, the question is, if at infinity the potential is 0, what is the potential inside the shell? Is it the same as the potential at infinity? That is 1. Is it different from the potential at infinity, etc.? Yes. Okay. So it's definitely constant. So everybody agrees that it is constant. So the question is it 0? That is the potential in the shell the same as the potential at infinity, or is it different? So that's what distinguishes 1 and 2. Okay, so we already said that the electric field is 0. Yes. One of the switchers. Why not? So your friend is saying that If we calculate the potential difference between some point in the center and at infinity, that potential difference will be, since the potential at infinity is 0, that potential difference will be the potential of my point inside the shell. And if I evaluate EDL, although E is 0 inside, there will be no contribution from inside, but I have a part of the path which is outside my shell where the electric field is non-zero, so there will be a finite contribution to my integral, and hence it will be the electric field, the potential inside will be constant, but it will be non-zero. He said the same thing. The potential difference, you are talking always about the potential difference will be 0, and hence the potential will not change inside. Well, it's basically the same thing. Your friend is saying that the potential difference between the surface of the shell and infinity is finite. So on the surface of the shell, the potential has a non-zero value. And inside the shell, since there is no electric field, there is no potential change. So inside the shell or on the surface of the shell, the potential will be the same. Since on the surface of the shell, the potential is non-zero, inside the potential is non-zero. No, it's not. Inside the electric field is 0. Inside is empty. True. No. Why should it be 0? Okay. No. You see, when you are evaluating E.dl, you should think about the electric field at every point on your path, not only at the start or at the end point. Electric field inside is of course 0. But along the path, as you come from infinity towards the center, there's all this region where you have an electric field. At least that is what they claim. Okay, you are losing more people. Okay, any objection to this claim? Okay. Okay, your friend is saying that, okay, inside the shell, there is no charge, so there shouldn't be any potential inside the shell. Do you agree or disagree? So they say that, okay, that doesn't make any sense. You should measure the potential difference relative to infinity. Why should we refer to infinity? Your friend is saying because we have fixed the potential at infinity to be 0. No, I didn't ask coming from infinity. I said the potential at infinity is 0. So if I rephrase his comment, he also says that if you choose the potential inside the shell to be 0, then the potential at infinity cannot be 0. That's what they claim. And their objection to that is, why do we bring the charge from infinity? We are at the center of this, inside this shell. No, I mean, at the moment that we enter into the shell, we don't do any work. Inside the shell is 0, electric field is 0. The potential difference is 0. Okay. No, that's not the question. The question, we are not looking at the potential differences inside the shell. We are looking at the potential inside the shell, not the potential difference. Now, since you said that inside the shell the potential difference is 0, you are saying that inside the shell the potential is constant. So everybody agrees on that. You say that the potential inside the shell is constant because the electric field is 0. You say that the potential inside the shell is constant because the electric field is 0. Now the question is, what is this constant? Is it 0 or non-zero? Or put in another word, is the potential inside the shell the same as the potential at infinity or different from the potential at infinity? Because we are taking infinity as our reference point. So you are in between. Okay, what is puzzling you? Okay. Okay, how can he determine whether it is 0 or not? Or is it the same as the potential at infinity or not? So, but basically, you're always repeating the same thing. So what they are doing is to determine whether the potential here is 0 or not, they are just calculating the potential difference between this point and the point at infinity. Since at the point at infinity, you are given that the potential is 0, the difference, the potential over here minus the potential at infinity is the potential over here. But that difference is nothing but the integral along a path that connects infinity to that point of E dot dl, the electric field. Here, out of the shell, electric field is non-zero, so E dot dl will have a non-zero value, and hence the potential difference between this point and the point at infinity will not be 0, and hence the potential of this point will be non-zero. That's what they are always saying. Yes. He is also adding that since inside the potential is constant in the shell, the potential at any point inside the shell is the same as the potential on the shell itself, because the potential difference inside is 0, which is unfortunately the correct answer. The potential is non-zero inside. We are not looking at the potential difference. The question is not asking you the potential difference. The question is asking you the potential, not the difference. Now, by saying that the potential is constant, you are all saying that the potential difference is 0 inside. There's no question about it. None of you have any doubts about that, apparently. But the question is, what is that constant value? Is it 0 or is it non-zero? Just reinterpret it. 0 just means, is the potential inside the shell the same as the potential at infinity? That is what the potential inside is equal to 0 means. Now, for example, in the question you could have been given the fact that the potential at the center of this shell is chosen to be 0. It's a choice. It's up to you which point to choose as your reference point. Now, in that case, the potential everywhere inside the shell will have 0 potential, because the potential inside is constant. If one point has 0 potential, all the points have 0 potential. But in such a case, the point at infinity will not have 0 potential. It will have a finite potential. Now, in the question, you are given that the potential at infinity is chosen to be 0. No, it's finite. The potential is finite no matter which point you choose as your reference point. The choice of the reference point is completely arbitrary. So that's why I'm saying that 0 mean the question, maybe the choices could be written as differently as 1, the potential inside the shell is constant and that constant value is equal to the potential at infinity, which we chose to be 0. Or it is constant but different than the potential at infinity. So this is choice 1 and choice 2. And since the electric field outside is non-zero, E dot dl will be non-zero. Okay. So you see, this is our spherical shell. You all agreed that inside the electric field is 0. Outside, you can write the electric field to be 1 over 4 pi epsilon 0 q over r squared in the r hat. Now, r vector position of the observation point relative to the center. Now, let's just take this point A. The difference between the potentials at the point A and the potential at infinity is nothing but minus from infinity to A of E dot dl. And let's say the radius is r. Now, if you evaluate this integral will just turn out to be 1 over 4 pi epsilon 0 q over r. Now, why? Well, outside the shell, it just acts like a point source. So you can just evaluate this integral up to the outer shell, just repeating the treatment we did for a point charge. And it will give you this result, exactly this one. And once you reach on the surface of the shell, inside the electric field is 0, so there's no contribution. So this difference is equal to this one. Or you can also say that V of A is equal to the potential at infinity plus 1 over 4 pi epsilon 0 q over r. The thing that is certain is that this potential difference is non-zero. So the potential at inside the shell cannot be equal to the potential at infinity. So that is the only thing we can say, in fact, without any more information. Now, if the potential at infinity is given to be 0, then the potential at any point inside the shell will be just 1 over 4 pi epsilon 0 q over r. It will be non-zero. Now, but of course, you are free to choose the potential at infinity to be minus 1 over 4 pi epsilon 0 q over r. It's up to you. It's a choice. Nothing should change if you change your choice. For such a choice, the potential at A will of course be 0. But in the question, you are told that the potential at infinity is 0. So if the potential at infinity is 0, then the potential inside the shell cannot be 0. It has this constant value. Any questions on this? Okay, so let's go back to our capacitors. So we have two capacitors. Now in charging the capacitor, what we do is we just take some charge from one plate and put it on the other one. Well, that is what in a given circuit, the different circuit elements, and we will be discussing the batteries shortly and what battery does. If you connect this system to a circuit, what will happen is the circuit will just take some charge from one end. So let's say that it takes a plus Q charge away from this wire. So what is left is a minus Q charge over here. And that plus Q charge, it will just bring it back from the other end, and it will put some plus Q charge over here. Now the question, what is the charge in this plate? It should be plus Q. All the minus Q charge will attract this plus charge from the other side. So this plate will be charged plus Q, and this other plate will be charged minus Q. Because the inside system, this conductor is neutral. It has to be neutral. It was neutral to start with. If we take minus Q charge, this minus Q charge will attract plus Q charge to the other plate. We're leaving this plate negatively Q charge. And you can also say that, okay, we have plus Q charge over here, it will attract this minus Q charge. A, B, C, and this capacitor, let's say, have capacitance C1, this capacitor has capacitance C2. Now, what is the potential difference between A and B? Potential difference. Q over C. Q over C1. Now, just a short note, a short way to remember whether it is Q over C or Q is equal to CV, etc. I'm afraid it's in Turkish, but when I was in high school, our teacher just told us that Q is equal to Cevat. Q is equal to C times V. Q is equal to Cevat. Okay. Now, what about B and C, the potential difference between B and C? Q over C2, it has the same charge on each plate. Now, we also know that VAC was nothing but VAB plus VBC. Now, we can just imagine, you see, the potential difference is this line integral, and you can just take this, consider this line, you start from A to, and you end up at C. You start from A, you end at B, that gives you VAB, and then you continue from B to C, that gives you VBC. The total line integral is the sum of the parts. Now, this is equal to, we already said that VAB is Q over C1, and VBC is Q over C2. So this is equal to Q times 1 over C1 plus 1 over C2. And remember, the charge that we have moved, that passed through our circuit is Q, sorry. This is the charge that moved our circuit. So we can define VAC to be equal to Q over the equivalent capacitance, provided that 1 over C equivalent will be equal to 1 over C1 plus 1 over C2. So what this means is basically if you have connect two capacitors like this, you can just replace it by a single capacitor who has the capacitance given by the C equivalent. They will do the identical job in the sense that if you move a charge Q from one side to the other side of this new single capacitor, it will create the same potential difference. And you will do the same amount of work, and the capacitor will store the same amount of charge, same amount of energy in the system. No, they store the same amount of energy. This one, C1, C2, behaves exactly like this one. You see, I'm not adding these capacitors one by one. I just connect these two capacitors and carry a charge Q from this one to this one. That's the only thing I do. If I do the same thing, and for this capacitor I take a charge Q from this end and carry it to the other end, at the end the amount of energy stored is identical. What was the amount of energy stored? 1 over 2 Q squared over C equivalent. This is the amount of energy stored in this one. This is equal to, from the definition of C equivalent, Q squared over 2, 1 over C1 plus 1 over C2, or 1 over 2 Q squared over C1 plus 1 over 2 Q squared over C2. This is the energy stored in capacitor 1. This is the energy stored in capacitor 2. So they have identical properties. They store the same. I mean, given that a charge Q flows through our circuit, they store the same amount of energy. They create the same potential difference. They behave identically. Other questions? Now this property, I mean, we will always use this symbol from the parallel plate capacitor, but what we drive is independent of the shape of the capacitor. Whichever capacitor you use, I mean, if you look at here. Now the capacitance is defined for any shaped capacitor. And the potential difference between the ends of the capacitor is always given by the charge divided by the capacitance. It's always whatever the shape of the capacitor is. So this result is also true independent of which capacitors you use. One can be a parallel plate capacitor, the other one can be a cylindrical capacitor, for example. The result will still be the same. Now let's connect the capacitors parallel. Now in this case we have these two capacitors. Again, this one, let's call it C1, this let's call it C2. Point A prime, point B prime, point C, and point D. Now, what is the potential difference between A and A prime? We are over here, A and A prime. Line is a conductor. It's 0. We are still in electrostatics. Remember, we are still in electrostatics. Although we are just moving charges around, we are considering the case when all the charges are at rest eventually. So when the charges are at rest, there won't be any potential difference between the point A and A prime. Because the electric field inside this conductor will be 0. Since the electric field inside the conductor is 0, I can just imagine a path that takes me from point A to A prime that goes through the conductor. Through the conductor, electric field is exactly 0, and this is 0. Similarly, the potential difference between B and B prime will be 0. So let's see, what about the potential difference between A and B and the potential difference between A prime and B prime? Why are they equal? Well, in fact, from these, we can just say that now VAB is, let's just define it as VA minus VB. VA prime B prime, this is equal to VA prime minus VB prime. So VAB minus VA prime B prime is in fact VA minus VA prime minus VB minus VB prime. But this is nothing but VAA prime minus VBB prime, and we just said that both of them are 0. Now, when we connected the capacitors in series, we said that the charges in each one of the capacitors is the same. But in this case, it is the potential difference across each capacitor is the same when we connect them in parallel, because both ends are connected by a conductor. This is our system. Now again, if we want to determine the capacitance of this system, what we need to do is we just move some charge from one end and dump it on the other end. So let's say we just take some charge Q from here and put it over here. There will be some charge on the first capacitor, let's call it Q1, and there will be some charge on the other capacitor, Q2. Q1 and Q2, they don't need to be equal. And what we carried some Q, now we have a potential difference between C and D, some potential difference which we will just determine in a moment, and this has to be equal to Q over C, equivalent. This is how we define the capacitance of a given system. We just carry charge from one end to the other one, let it build a potential difference between these two ends, and the relation between the potential difference between the ends is equal to charge over the capacitance. Or the total charge should be equal to C equivalent times VCD. Now the total charge is Q1 plus Q2. Now we already said that VAB is equal to VA prime B prime, which is also equal to VCD. Let us just call it V. Because in fact A prime and C, they all have the same potential. B prime and D also all have the same potential. So any potential difference between one point over here and one point over there, they have the same value, which we can just call as V. Now we know that Q is equal to C equivalent times V. Now Q1, well, Q1 is around on a capacitor which has capacitance C1 and potential difference V. And Q2 is on a capacitor with capacitance C2 and potential again VA prime B prime, which we defined as V. So equivalent capacitance in this case is nothing but C1 plus C2. Now for a parallel plate capacitor, these are kind of easy to interpret. This equation is true for any capacitor, whatever the shape of the capacitors are. For a parallel plate capacitor, let's say this distance is D1, this distance is D2. Let's say that they both have the same area. So inside they have identical electric fields. No, these will be different. Can be different, I don't really care. But effectively, this is the same thing as this is D1 plus D2. But we know that C for a parallel plate capacitor is proportional to one area over the distance. So the capacitance of this one, let's say 1 over the capacitance of this one, which is proportional to D1 plus D2. 1 over capacitance 1 is proportional to D1. 1 over capacitance 2 is proportional to D2. So you already see that since you are adding the D's over here, 1 over the equivalent capacitance should be equal to 1 over the capacitance of the other capacitors. This is when you connect them in series. Now when you connect them in parallel, you have a similar relation. Now in this case I will assume that they have the same, since these capacitors have different capacitances, that's why they cannot have the same area and same separation. Now in this one I will assume that they have the same separation. This will have area A1 and this will have area A2. If the separation are the same and they have different capacitances, that just means their areas have to be different. But this is the same thing as this one. The same area, the same separation, but the area is A1 plus A2. We are summing the areas. And remember the capacitance, if D is constant, is proportional to the area. So equivalent capacitance is equal to C1 plus C2. Because these C's are nothing but just A1 times some constant, C1. C2 is area times the same constant, and C equivalent is the equivalent area times exactly the same constant. So you can just think of this, at least for the case of parallel plate capacitor, you can think of our results on series connection and parallel connection to just a consequence of the fact that either we are adding areas or we are adding the separations. So you are saying that I have a capacitor like this, and inside I put another capacitor like this. Well, these are two capacitors. This is one, this is the other one. So you are saying that I have such a capacitor, this configuration. Well, these will not do anything. These will have no effect. But then you can ask the question, what happens if we put some material over here? Some dielectric. Insulator. We will see whether it makes any difference or not. It does make a difference. Next hour. I mean, this dielectric thing we will be discussing next hour. In this one. In this one, you mean, here we have a large plate, here we have a smaller one, here we have a smaller one. Well, you see, again, nevertheless, these are two capacitors. You have to calculate the capacitances. If the plates have different areas, it will be hard to calculate the capacitances. But once you calculate them, these results will be valid. I mean, in these results, we are not making any assumption about the shape of the capacitor. It's just some system is over there. It can have arbitrary complicated shapes, whatever shape they can have. The thing that we know is we know their capacitances. If we know the capacitance of each one, then we can calculate the capacitance of the combined system, independent of how complicated the internals can be. Let's see. Energy in parallel connection. U is equal to 1 over 2 CV squared, or C equivalent times V squared, which is 1 over 2 C1 plus C2 times V squared, 1 over 2 C1 V squared plus 1 over 2 C2 V squared, or the energy stored in the equivalent capacitor is equal to the energy stored in the first capacitor plus the energy stored in the second capacitor. The same thing. Now, of course, there is a trick that I did. I don't know if you have paid attention to. In the previous derivation, I used U is equal to 1 over 2 Q squared over C. In this derivation, I used U is equal to 1 over 2 C times V squared. Yes, because in the previous expression, the Q is the same for both capacitors. Now the V is the same for both capacitors. Of course, I can use this expression also here. No problem with that. But I have to pay attention to that the Q of the total equivalent capacitor is also equal to Q1 plus Q2. No, it's not. I'm not saying that nothing changes. No. Energy also changes. Here, the only thing we are proving is that energy-wise, these two capacitors connected either series or in parallel is the same thing as both of these capacitors replaced by their equivalent capacitors. But the energy stored will be different. Remember, if you consider in series, C equivalent is equal to 1 over C1 plus 1 over C2 inverse, or C1 times C2 divided by C1 plus C2, which is less than both C1 and C2. In parallel, C equivalent is equal to C1 plus C2, which is larger than both C1 and C2. If you connect two capacitors in parallel, they have a larger capacitance. If you connect them in series, they have a smaller capacitance. So if you want to, for example, let's suppose that you create a system. You take a battery. A battery is a device which just keeps constant potential difference at the two terminals. That's the definition that we will use for the battery for the time being. So let's say we have a battery. We have this system. The total energy stored is, let's say, U1. And we have exactly the same battery, and we connect it here. Which one of these systems have a larger potential energy? This is U2. Remember, U is equal to 1 over 2 C V squared. Now, V is the same in both of these. because we are connecting them to the same battery. So whichever one has a larger equivalent capacitance, this one has a larger potential energy. So U1 is larger than U2. We will see. I mean, what are you doing? What kind of work are you doing anyway? You are not using the battery. You just stored some energy. For example, one thing you can do in these systems, you can use the capacitors to increase voltage. For example, you have a battery that is, let's say, 1.5 volts, but you want to create maybe a very short potential difference of, let's say, 6 volts from one battery. What you can do is take 4 capacitors, equal capacitors, first connect them in parallel, charge them. So across the capacitor you are building 1.5 volts. Then you connect them in series. So in total you will get 6 volts. Yeah, for example. Well, capacitors have many other applications in dynamics, not in electrostatics like this one. For example, to get the flashes working, you need a huge potential difference. But you create them from 1.5 volts. Yes. The flashes on your cameras, they work with 1.5 volts. You still need a large potential difference. Or another thing that you can do, you can mechanically squeeze them. What happens when you squeeze them? Do you increase the energy or decrease the energy? Yeah, I mean, you have this parallel plate capacitor, so you exert a force on them, reduce their distance. What happens to the capacitance? You are decreasing the capacitance, charge is the same, so V, the potential difference, is increasing. Right or wrong? So what happens when you squeeze a capacitor? What happens to the potential difference? Okay, this is for you to think during the break.